In this video, we are going to discuss about the insertion of an AVL tree. See, in the previous video, we already have discussed what is an AVL tree, why we need an AVL tree, and what all the operations that we can perform, what all the different kinds of rotation we can perform in an AVL tree. So in this video, we are going to discuss about, like I just take some examples. So this example covers all possible criteria for rotations. And I'll show you how to insert all the elements into a AVL tree. And before that, we know that insertion, like after each and every node of insertion, the AVL tree we have to verify the balance factor for the AVL tree. And it has to lie between either -1 to 1, either -1, 0 or 1, not less than or not more than this. Okay, so first node to be inserted is 70, and that will act as the root node. So 70, we just create it as a root node. When there is only one node, balance factor will be 0. There is no left subtree, there is no right subtree. So no need to calculate the balance factor here. Now, when you want to insert the second node, 100, check the value of 100 with the root node. So the root node value was 70, 100 is greater than 70. So you have to insert that as the right side child for 70. Now, when you verify the balance factor for 100, there is no left subtree or right subtree. The balance factor will be 0. And for 70, there is no left subtree and the height of right subtree is 1. So it is 0 minus 1, the balance factor is -1. So when it lies between 0, -1 or 1, it doesn't matter. The tree is in a balanced structure. So we don't want any rotation over here. So the next node to be inserted is 110. Again, compare the values. So we need to insert 110. 70 is lesser than 110. So 110 has to be inserted to the right of 70. And in right side, we already have a node. Okay, and the value of node, the right node is 100. Now compare the node of value 110 with 100. 110 is greater than 100. So you have to insert it as the right child for it. Now calculate the balance factor for the leaf node. The balance factor is 0. And for this node, there is no left subtree, and the right side subtree, the height is 1. So the balance factor is 0 minus 1, it is -1. And for 70, you don't have any left subtree. The height of left subtree is 0. And the height of right subtree is, take the longest branch that reaches to the leaf node. So this is the longest branch, and the number of edges will be counted. So the height is 1 plus 1, it is 2. So the balance factor is 0 minus 2, height of left subtree minus height of right subtree. So 0 minus 2 is -2. As per rule, the balance factor should lies as either -1 or 0 or 1. Okay, but the balance factor for 70 is -2. And this actually happens due to the imbalance occur to the right of insertion. Okay, so -2 actually indicates the imbalance actually occurs to the right side of it. So it is right to right. We have to perform an anti-clockwise rotation, RR rotation. So how we perform an anti-clockwise rotation here? So 100 will remain as it is, and 110 will remain as the right side child for 100. These two will remain as it is. And we are going to pull 70 down as the left side child for 100. So this is how an RR rotation happens. So 100 and 110 will remain as it is. 70 will be pulled down. Now this is a balanced tree. Now calculate the balance factor. For 70 it is 0. For 100 it is 110 it is 0. And for 100 you have 1 left subtree. Height of left subtree is 1. Height of right subtree is 1. So it is 1 minus 1, 0. Okay. So this is the balance factor. For all the nodes are 0. So it is perfectly balanced AVL tree. Now 3 nodes are inserted and we performed 1 rotation RR. Now we'll try to insert the next nodes. I'll just remove the balance factor alone. The next node to be inserted is 140. So how will we insert 140? First, we have to compare 140 with the value of root node. 140 is greater. So you have to traverse to the right side. Now compare the value of 140 to 110. 140 is greater. So you have to add that as a right side child for 110. Okay, now calculate the balance factor. For 140, it is 0. There is no left child, right child. And for 110, what is the balance factor? Left subtree, 0. and the height of right subtree is 1. So 0 minus 1 is minus 1. For 70, there is no left subtree, right subtree, the value is 0. And for 100, what happened? The height of left subtree is 1 and height of right subtree is 2. So the balance factor is minus 1. So the balance factor for all the nodes should be either 0 or 1 or minus 1. So it satisfies the condition. So we'll keep on inserting the next node. So the next node to be inserted is 90. So how will we perform an insertion for 90? First, compare the value of 90 to the root node. The value 90 is lesser than root node. So you have to perform an insertion to the left subtree of 100, traverse to the side, and compare the value of 70 and 90. And 90 is greater than 70. So you have to add it as a right side child for 70. Okay, now calculate the balance factor. For the leaf node, it is 0, no children. And for 70, left side subtree, it is 0. And right subtree, the height is 1. So 0 minus 1 is minus 1. And for 110, no left subtree and 1 right subtree, it is minus 1, 0 minus 1. And for 100, the height of left subtree is 2. So you have to calculate, take the longest branch that reaches the leaf and calculate the number of edges. So this is the longest branch and the number of edges here is 2. And for right subtree, again, take the longest branch that reaches the leaf node and calculate the number of edges. So it is 2. 2 minus 2 is 0. The balance factor for 100 is 0. Now the balance factor is either 0, minus 1 or 0. It is all fine. Okay, no need for any rotation here. Now take the next element to be inserted. The next element to be inserted is 80. So how can you perform insertion here? Compare 80 with 100. 80 has a lesser value. So you have to traverse left side. Compare 70 and 80. 80 value was greater than 70. Traverse to the right side of it. Now compare 80 and 90. 80 value was lesser than 90. So you have to add it as a left side child for 90. Now calculate the balance factor. For 80, it is 0. And for 140, it is 0. And for 90, the height of left subtree is 1. Height of right subtree is 0. So the balance factor is 1 minus 0. And for 70, there is no left subtree. Okay, so it is 0 minus height of right subtree is take the longest branch that reaches to the child leaf node. Okay, and the number of edges is 1 and 2, it is 2. So the balance factor is 0 minus 2, it is minus 2. For 70, it is minus 2. And for 110, what happened? There is no left subtree and only one right subtree. So the balance factor is 0 minus 1. And when you take 100, how can you calculate the height of left subtree? Take the longest branch that reaches to the leaf node and find the number of edges in it. 1, 2, 3. 3 edges are connected to the left subtree. And to the right subtree, 1, 2. 2 edges. So it is 3 minus 2 equal to 1. So the balance factor for 140, 110, 100 and 80, 90, it is all same. But the problem is it is all balanced. But the problem is for 70, we have minus 2. So what does minus 2 means? There is an imbalance occurs. The balance factor should lies as either minus 1, 0 or 1. It should not go a minus 2 or 2 is not allowed here. So what we have to do? We have to perform a rotation here. And what kind of rotation is needed? The imbalance to the imbalance occurs as minus 2. Minus 2 actually means there is an imbalance to the right side and right to left. So we need an RL rotation to be performed. Right? Whenever it is minus, the imbalance is the tree is imbalanced to the right side of the node. Okay, so it is minus. Minus actually denotes it is right side tree is more. Okay, the balance factor is calculated as height of left subtree minus height of right subtree. So when it is minus, the right side subtree has a value more than, the nodes more than, the height more than it is needed. Okay, so we have to perform RL rotation here. And how we perform RL rotation there? So we have to do twice. Okay, so first we have to convert this RL rotation in terms of RR, and then we have to perform an anti-clockwise rotation. Okay, so I'll just draw this node separately. You have 70 and you have to perform an internal rotation between this 80 and 90. So it will be taken as 80, 90 here. The property of binary search tree should not failed over here. 70, 80 is greater than 70, so it lies in the right side, and 90 is greater than 70 and 80, so it lies in the right side of it. Now it becomes RR category. So how can you perform RR rotation? And anti-clockwise rotation to be performed. Okay, so 80 will remain as it is, 90 will remain as it is, and this 70 will be pulled down. Okay, 70 will be pulled down to the left side child for 80. Okay, so now we have to insert that into this branch. So this 100, 110, 140 will remain as it is. And in this branch is modified as 80, 70, and 90. Right? So we performed a rotation, RL rotation. So first we perform RR rotation, and here we perform RL rotation here. Okay. So finally calculate the balance factor for all the nodes. For all the leaf nodes, balance factor is 0. And for 80, the height of left subtree is 1, height of right subtree is 1. So it is 0 here. And for 110, there is no left subtree, and the height of right subtree is 1. So it is 0 minus 1 minus 1. And for 100, height of left subtree is 2, height of right subtree is 2. It is 2 minus 2 is 0. So all the nodes will have either minus 1, 0, or 1. So it is perfectly balanced AVL tree. Okay, so with that, we're going to insert the next node. The next node to be inserted is 50. So I'll just erase all this balance factor. Now insert 50. How can you insert 50? Compare the value of 50 with the root node. The value 50 is lesser, traverse to left. Compare 80 and 50. It has the lesser value, traverse left. 70 and 50, the value is lesser. So you have to add it as a left side child for 70. Now calculate the balance factor. For 50, it is 0. For 70, 1 left subtree, and there is no right subtree. So it is 1. 1 minus 0. And for 90, all the leaf nodes will have 0 balance factor. And for 80, what happened? For 80, left subtree height is 2 and right subtree height is 1. So it is 2 minus 1, 1. And for 110, there is no left subtree and only one right subtree, height is 1. So it is 0 minus 1, it is minus 1. For 100, the left subtree height is, take the longest branch that reaches to the child. So the longest branch consists of 1, 2, 3 edges. So the height of left subtree is 3 and the height of right subtree is 2, equal to 1. So all the balance factor is either 0 or 1 or minus 1. So it is perfectly balanced AVL tree. All the balance factors satisfied. So we'll perform the next insertion. So the next element to be inserted is 40. And where we have to insert 40? 40 is lesser than 100, lesser than 80, lesser than 70, lesser than 50. So you have to add it to the right side corner. The element will be added at the end. So now calculate the balance factor now. So for 40, all the leaf node balance factor will be 0. And for 110, no left subtree, only one right subtree. So it is minus 1. Now for 50, what happened? You have an imbalance occur here. Sorry, you have one left subtree, no right subtree, balance factor is 1. And for 70, you have 2, right? For 70, you have the height of left subtree is 2 and height of right subtree is 0. So it is 2 balance factor. And for 80, what happened? The same thing, right? So you have the balance factor for 80 is, height of left subtree is 1, 2, 3. And height of right subtree is 1. So 3 minus 1 is 2. And for 100, height of left subtree is, take the longest branch and calculate the number of edges. It is 1, 2, 3, 4. And take the longest branch in the right subtree, 1, 2. So the balance factor is 2. Now the imbalance occurs to this place, so you have to perform an RR rotation. Okay, so how we perform an RR rotation? So here we have to make a clockwise rotation towards this place. So when you make a clockwise rotation, what happened? This will occurs like 50 will become the root node and will be having 40 and 70 will be pulled down. So the structure will be varied like this. Okay, so I'll redraw the diagram over here. Hundred, 80. Now these plays it is modified. So this total plays is modified as 50, 40, 70, 90, 110, 140. Okay, so even after rotation, since we had an imbalance in more than one places, so you have to do it again. You have to try calculate the balance factor again for this nodes. And if there is no modification, you can keep on. Like if the balance factor lies is either 0 or -1 or 1, we can directly proceed with next insertion. So for all the leaf nodes, the balance factor is 0. And for the node 50, you have one left subtree, one right subtree. The height is 1 minus 1, it is 0. The balance factor is 0. And for 80, the height of left subtree is 2 and the height of right subtree is 1. So 2 minus 1, the balance factor is 1. And for 100, the balance factor is the height of left subtree is 1, 2, 3, and the height of right subtree is 2. It is 3 minus 2, the balance factor is 1. So all the balance factor are either 0 or 1 or -1. So it fully satisfies your binary AVL tree property. So next we'll proceed with the next insertion, that is 30. So where we have to insert 30? So 30 will be comparing the value of 30 to 100. 30 is lesser. Again, traverse left. 30 is lesser than 80. Traverse left. 30 is lesser than 50. Traverse left. And 30 is lesser than 40. So you have to add 30 over here to the left side child for 40. Now calculate the balance factor. For all the leaf nodes, the balance factor will be 0. And for 110, there is no left subtree, only one right subtree. 0 minus 1, the balance factor is -1. And for 40, one left subtree. The height of left subtree is 1 and no right subtree, so the balance factor is 1. And for 50, the height of left subtree is 2 and height of right subtree is 1. So it is 2 minus 1, it is 1. And for 80, the height of left subtree is 1, 2, 3. Okay, so 3 is the height of left subtree and the right subtree height is 1. So it is 3 minus 1. The height of left subtree is, for 80, it is 2. Okay, so what happened with 100? The height of left subtree is, take the longest branch, it is 1, 2, 3, 4. 4 over here. And the height of right subtree is 2, -2. So the balance factor is 2 here. Now it is an imbalance criteria. Now we have two places where the imbalance occur and we take the lowermost place. So here it is 2. 2 actually means to LL. Where the imbalance actually occurs, to the left the imbalance actually occurs. So you have to perform an LL rotation towards this place. Okay, so then like you have to consider the node that where the imbalance occurs. So for 80, you have the imbalance and it is to the left. And the insertion actually happens to the left. With these three nodes, we have to perform a rotation. So when you are performing a rotation with these three nodes, it is to the clockwise. It is LL criteria, right? You have to perform a clockwise rotation. So when you are performing clockwise rotation, 50 will become 50 and 40 will remain as it is. And we have to pull 80 down. So 80 will be moved here and listen carefully. 80 will be moved down and 90 is there as the right side child for 80 that will remain as it is. Now what we do with this 70? That is very important. So we are just making this as a root node. So 80 will be pulled down. So 80 will be the left side child for 80, so 50. And what about 70? This 70 will be added to the right side, sorry, left side child for 80. 70 value was lesser than 80 and it is greater than 50, so it is added over here. So this is how we perform a rotation. So we should not ignore any of the nodes in between. And the 30 that is present over here will remain as it is. Now I'll draw the entire tree structure. So 100 will remain as it is. 110 will remain as it is. And 40 also will remain as it is. And towards the side, we performed the rotation, and this is the branch that we had after rotation. So 50, 40, 30, and towards the space you have 80, 70, and 90. Okay, so everything are there in the place. Now when you calculate the balance factor for all the leaf nodes, the balance factor is 0. And for 110, no left side child, height of left subtree is 1. And for 80, height of left subtree, height of right subtree, both are 1. So it is 1 minus 1 is 0. And for 40, height of left subtree is 1. No right subtree, so it is 1. And for 50, height of left subtree is 2. Height of right subtree is 2. 2 minus 2 is 0. And for 100, height of left subtree is 1, 2, 3. And height of left subtree is 1, 2. So it is 3 minus 2 equal to 1. So all the balance factor are either 0 or 1 or minus 1. So not an issue. Now we'll proceed with the next insertion. The last node to be inserted is 35. So 35 lesser than 100, lesser than 50, lesser than 45, and it is greater than 35. So you have to add it over here to the right side child for 30. Now calculate the balance factor. For 35, all the leaf node, it is 0. And for 80, one left subtree, one right subtree, it is 0. And for 110, it is minus 1. And for 30, no left subtree, one right subtree, right? The balance factor will be minus 1. And for 40, left subtree height is 2 and right subtree it is 0. So it is 2 here. And for 50, what is the balance factor? It is 1, 2, 3 over left and 1, 2 over right. So the balance factor is 1. And for 100, take the longest branch that reaches the leaf node. This is the longest branch. And what is the balance factor for the longest branch? It is 1, 2, 3, 4. 4 over here and 2 in this side. 4 minus 2 is 2. So the balance factor doesn't matches over here. The balance factor should be either 0 or 1 or minus 1. So here we have two balance factors. So we have to perform a rotation. So what kind of rotation to be performed? So we have to check the imbalance criteria over here. So here we have an imbalance. So first we'll rectify it and we verify whether the balance factor over here is adjusted or not. So here it is ALR category. To the left of it, to the right of it, and you have to perform twice. The rotation has to be performed twice. So first internal rotation has to be performed between these. So we'll be having 35 and 30 attached to 40. Okay, so it will become LL and you have to perform a clockwise rotation here. So 35 will be the root node and you'll be having 30 here and 40 here. Okay, so whenever it is an LL or LR, you have to perform it twice. Okay, so done. Now next. Now we attach this branch over here and check whether the imbalance is rectified or not. 100 root node, 110 here and 40 here. And 50 will remain as it is. For 50, you have a branch over here, 80, 70, 90 as it is. And this side we have made a rotation. So you'll be having 35, 30 and 40. Okay, so now all done. Calculate the balance factor. So start from all the leaf node, balance factor is 0. And for 80, 1 minus 1. So it is 0. For 35 also 1 minus 1, 0. And for 50, the balance factor is left side height is 2, right side height is 2. It is also 0. And for 110, no left side, only right side child is there, -1. And for 100, the balance factor is 1, 2, 3. Height of left side is 3 and height of right side is 2. 3 minus 2 is 1. Got it? So all the balance factor lies as either 0 or 1 or -1. So this is how an insertion actually happens. So we have to calculate the balance factor for each and every time, and you have to perform an insertion or you have to perform a rotation accordingly. Okay. So one more insertion alone I'll perform to make it sure like you understand it better. So I'll just insert one more element 10 into this list. So what happened when I insert 10? 10 is lesser than all the nodes, so it will come over here. Now what will be the balance factor? For this node it is 0, and for this node it is 1 left side child. So it is 1. And this is 0, and the balance factor for node 35 is height of left side is 2, height of right side is 1, so it is 1 here, 2 minus 1. And for 50, height of left subtree is 1, 2, 3, and height of right subtree is 1, 2. So it is modified as 1 here, right? 1, 2, 3 minus 1, 2. And for 100, what will be the balance factor? The height of left subtree. Take the longest branch that reaches the leaf node. So this is the longest branch, and the number of edges are 1, 2, 3, 4. 4 here in the left subtree, and for right subtree it is 2. 4 minus 2 is 2. Now tell me what kind of rotation is needed over here. So the imbalance actually occurred to the node 100, and the imbalance value was 2. So where we want to perform the rotation from this node to the left to left, right? When it is 2, it means that the imbalance is in the left hand side. When it is in the minus value, the imbalance is in right side, and when the imbalance is 2, it is in the right side. Okay, so it is left to left. Now you have to perform a clockwise rotation over here. So 50 will be the root node, and 35 will remain as it is. So whatever branch we have after 35, like you have 30 here and 40 here and 10 towards it, it will remain as it is, and we'll be pulling this 100 down. So 100 will come as the right side child for 50. Okay, so 100, and this 100 is attached with 110 remains as it is, and 40 will remain as it is. Now, only thing that you want to take care of it is where to attach this branch. That branch that actually exists as the right side child for 50 will be attached to the left side child for 100. Since this 100 is the node that is pulled down, it doesn't have any left child. Okay, so we'll be attaching this 80, 70, and 90 towards this place. Now you can calculate the balance factor. Like by seeing this tree, we know that it is balanced. So all this leaf node will have 0 value. Balance factor for 110, it is -1. For 80, it is 1 minus 1. And for 100, the height is 2. 2 minus 1, 2 minus 2, it is 0. For 30, 1 left child, it is 1, no right child. And for 35, the height is 2 minus 1, it is 1. And for 50, the longest branch to the left side is 1, 2, 3. And here also it is 1, 2, 3. For 50, the balance factor is 3 minus 3, it is 0. The balance factor actually lies between either 1 or 0 or -1. It is all fine. Okay, so this is how an insertion actually happens in AVL tree. So insertion actually works based on your binary search tree. You have to take the value, compare the value with the root node, and either traverse left or right accordingly. And once after the insertion has happened, you have to calculate the balance factor for each and every node. And if the balance factor is either 0 or 1 or -1, no changes is needed. The tree is balanced. But if it goes like 2 or -2, then you have to perform the rotation. Always prefer to rotate it at the end, and then we can, like when there is an imbalance occurs in 2 or 3 places, it is preferable to take the least one first and try to try to rotate it in the least pattern. Okay, so here also, like we have a few cases where the imbalance occurs in 2 or 3 places. We take the least branch, rotate it, and try to compare the check the balance factor. Even after comparing that balance factor, if the topmost haven't resolved, you have to perform the rotation again. Okay, So from the node where you have to do the where the imbalance occurs, you have to check whether it is LL or LR or RL or LR. Then you have to perform the rotation accordingly. Okay, thank you so much.